interruption in the network, so no worry. So we were just going through the diastereoisomers and stereoisomers apart. So hope you guys noted it down, right? So I have sent certain recordings also. So you see that again. So as per the network problem, now isomers are making different compounds by using the same molecular formula. That's the main concept here. So this can be divided into two. One can be structural isomers, and this can be constitutional isomers also. In structural isomers, you have position isomers, then you have function isomers. In stereoisomers, you have two. One you can say enantiomers. Okay. So in diastereoisomers, you know, things first you need carbon double bond. First thing. Second thing is that the groups that you have between the carbon bond. That is the important part you need to know. So while I was discussing it, got interrupted during network. Here you should know that if you take another symmetry, if you take another mirror image, this B will be up and this A will be down, right? If it is a mirror image, it will be like this. If you keep the mirror like this, you will get the same image like this, right? So this is the thing. Here this is non-superimposable. That's the case here. You can't impose it over here. You can ask me, sir, what if it comes like this? If it comes A, B and C. If you keep the mirror, see here, it's like a diastereoisomer. I will say no. Why? Here you have two identical groups in the mirror image as well as in the. So here, since there's two different changes, you can't consider be a diastereoisomer. Some of you can have a doubt. You can ask me, what if, sir, if it comes like this, what if all the sides have different groups? Yes, then that is also correct. This one can be a diastereoisomer unconditionally. Okay? Without any conditions, you can say this one is a diastereoisomer. Right. Now see, if the particular compound is like this, what is the name that you can give? And if this compound is like this, then what is the name you could give? If it is in same phase, in Latin we would say cis, cis. If it is on a diagonal way in opposite direction like this, we would say trans. And this is obviously trans isomer, right? So there is that thing you need to know, right? Right? So obviously this is how let's go with the enantiomers. Enantiomers. In enantiomers, you need to know that there is one more condition that you need to know. There are some conditions. First things first, you need to have an asymmetric carbon. You can say asymmetric carbon or chiral carbon, right? You can say this one as asymmetric carbon or chiral carbon. So there should be an asymmetric carbon. So you can remember this word which is coming in biology. Actually, you know which place it comes under proteins, right? Proteins. If there's an asymmetric carbon, then obviously the groups around the chiral carbon is a must to be different, right? For example, if you take the structure of protein, so you have right. So I was just discussing the statements, right? Which statement is necessarily true. So these are the conditions that you need to know when it comes to enantiomers. So it can be different groups in this way. If you put the mirror, it will be in this way. Okay. Now here, which statement is necessarily true of isomers? So in isomers, necessarily true means completely true, right? It has to be, it is a must to be true. It should be true. So in the first statement, they are hydrocarbons. It is in a must. In isomers, see here, in the geometrical isomers, you have this group, right? You have this changing group. And see here in this, you have different groups. You have carboxyl group, amine group, this type of a protein. In the same case, everything is different. So you can't say they must be a hydrocarbon. So exactly the statement is wrong. They yield the same products when completely burned in oxygen. So I am just keeping the statement because you have this group also now. So I'm just a quite puzzled part. Let's see what will happen. So finally we'll decide whether second answer is correct or not. They contain same functional group. So you know that in structural isomers, we already knew that there are three types. So one is functional group isomers, positional isomers, and finally chain isomers. In each of these cases, you must remember that there must be anything that can be changed in the functional group with respect to their molecular formula. Right? You can have either aldehyde or ketone. So 1, 2, CH, sorry, fellow. You can have this fellow. So you can have both aldehyde and ketone, right? There, it is a it is in a third statement is also wrong. They are optically active. And it is in a must. This is also an isomer now. This has to be isomer now. They are asking what? It has to necessarily be true. It is a must to be true. They can be optically active or optically inactive. This is optically inactive, this group. So fourth statement is also not a must. It is not the same structural formula. So isomers are, they should have same structural formula, right? So it is true because it is necessarily true. Why? Because from them only you can make different compounds. That's why we got isomers definition. Different compounds can be prepared from the same formula, same molecular formula or structural formula. So accordingly, you can say fifth answer is the correct answer, right? The fifth answer is the correct answer, right? See how the question has come in the term papers, right? The FWC papers and all, right? Let's see your next question. Okay, now since you know IUPAC nomenclature, right? Since you know the IUPAC nomenclature, we'll try this question. IUPAC nomenclature. Okay. Now see, which of the following, 15 MCQ, which of the following is true regarding the compound? But means 4. 1 chloro, 1 nol. So consider any one of the carbon. If I take this one as 1, 1, 2, consider this one as 1, 1, 2, 3, 4. So I will take this one as my hydroxide group. All, right, all means OH, 1 ol and 1 chloro. So let 1 Cl be here. Right? 2 butene. If this is 1, 2. So in second carbon, the double bond has been started. That is why in the IUPAC nomenclature also I have explained you in which carbon the double bond is starting. At that carbon only what you have to do, that numbering system, that numbering has to be there. Same way here. So here it is starting in second carbon. So 2 double bond, 1 nol, 1 chloro, 1 nol, butene, 2 in. So this has to be H3H, H. Right? This is the compound that they are asking regarding isomer. So this is actually double bond. So you can change them, right? So here this has to be H. So CH3, right? C, double bond C, H, H, C, OH, H, Cl. Understood? So this is the way the compound is being seen. It exhibits diastereoisomers. Does it show diastereoisomer? Yes, see here. You can find the change over here. This is being in this way. Right? This is being in this way. You can write this one in other way also. CH3, C double bond C, COH, Cl, H, and here you have an H, and here also you have an H. So this is trans, and this is cis. You can write it this way. How cis came? This is cis. Understood? It has, right? See here, first statement, second statement. First statement, they just said only Diastereoisomers, right? There are two compounds, okay. It exhibits enantiomers. Enantiomers means they should have optical isomers, right? They should have optical isomers. Now see, we have an optical isomer. Can you find out which carbon we have? This carbon has optical isomer. How? All these groups are different. See here, they have Cl, they have OH, they have H, and there is another group. So they have optical isomer. But what's the question they said? It has two chiral centers. See, we have 4 carbon. For showing optical active, all the 4 groups must be different. They can be 3 bonds or 2 bonds. Only 4 bonds should be there for optical isomer, right? Which means it should have 4 groups differently for a chiral carbon. Here you have 3. Here you have 3. Here you have 4. But all these 4, only one group is different, others all are same. Here you have 3 hydrogens here. So obviously that statement is also wrong. We keep 1 and 2. Still we are out. See the 4th one. It exhibits both diastereoism, stereomerism and enantiomerism. Exactly correct. See here. Here you have a chiral carbon. So which means you have enantiomers. You have an enantiomerism. Right? You have an enantiomerism. At the same time, completely you have a diastereoisomers also. Right? You have a diastereoisomerism also. Diastereoisomerism also. So you have both. Right? So in this, it exhibits both diastereoisomerism and enantiomerism. So obviously this is correct. So what is the answer? 4th is the answer. Next one. It exhibits neither diastereomerism nor enantiomerism. That is impossible now. We already found out that we have two. They can't say they both don't have, right? They don't have both of these merism, right? So obviously what is the answer? 4th one is your answer. Understood? This is the way you have to analyze the question. Analyze each of the statement, right? This is how you have to study the organic chemistry as well as the other subjects also. Learn to analyze each statement. Then you can study. Right? So let's see another question in the tube. Then we have statement question. In the statement question, you need to know what's the reaction going on, right? Without knowing the reactions, you can't do. So you have second question. Then you have third question. You have 4th question. Sorry, not 4th. Then you have 5th. 6th question. 8th question. 8. The correct statement or statements regarding stereoisomers of organic compounds is so up. So this came actually from Moratu paper last year. Moratu paper. Right, let's see the first statement. A. Let's see the A part. Enantiomers, isomers, stereoisomers having a structure that are not mirror images of each other. See the statement again. Enantiomers are stereo having the structures which are not images of each other. This is exactly wrong. Why? I said diastereoisomers are the ones. See, this is why we say the importance of reading resource books, right? They have given the exact point which is there in the resource book. See here carefully. The stereo isomers are the ones that they have not any mirror images. The mirror images are not equal. They don't have not mirror images, right? They have no mirror images. But in the case of enantiomers, they have mirror images. Not the points, right? There is space given in the tute also, right? There is extra places given to you. Not the points also, right? Special points are given space there. Use that also, right? So obviously a statement is wrong. Obviously a statement is wrong, right? For a compound to exhibit isomerism, the two groups attached to each of the double bond carbon must be the same. For a compound to exhibit geometrical isomerism, the two groups attached to each of the double bond carbon must be the same. Is it true? Let's see. What if the compound that we take contains different groups? Let's say HCl, Cl, Br and F. For example, this is also showing isomerism, geometrical isomer. This is also geometrical isomer. How can you say that they must be the same? Is it possible? It isn't possible. See, this is also geometrical isomer, but all the are not the same. They are different. So obviously, B statement is also false, right? In diastereoisomers, C statement, right? In diastereoisomers, right? In diastereoisomers, if the same groups lie on the same side of the plane, perpendicular to the plane of the molecule. They are saying it like this. Now see, if I draw the structure, right? Let me take a structure like this way, and let's complete it. Of the molecule, it is called cis isomers. Okay, now see, this is how your 3D structure will be, right? This is how the 3D structure will be. Right? So let's say this is hydrogen. Right? Wait a minute. Let's say this is hydrogen. This one is carboxylic acid. This one is carboxylic acid. If I draw a plane like this, right? If I draw a plane, if I just tilt it to a side, just like the paper, think it this way. Now this is my molecule I have. I'm just taking in this manner, right? In this manner, I'm just taking to this view and to this perpendicular, to this plane perpendicularly. So how it will be? It will be like this, right? This is going to be a perpendicular plane with respect to this plane. So if these two groups are in one side, they are called cis. So what did I say? In this case, in the 15 MCQ, if both the groups are in one side, what you can say? They are cis isomers. This is cis isomers. So obviously, C statement is correct. Enantiomers have the ability to rotate the plane of the plane polarized light. Okay, I forgot to say another important point. Enantiomers, another name is optical isomers. That you got right. In enantiomers, students, keep in mind, you have different groups here, right? Here you have different groups, right? I'm taking the previous questions structure. These different groups will have different image, right? We have a mirror image to the other side. This mirror image will have a rotation. If we use a polarimeter to this particular compound, there is an instrument called polarimeter to observe the optical rotation. So if you put the polarimeter to this place, there will be a rotation. It can be either clockwise direction, no anti-clockwise direction. It can be a clockwise direction or an anti-clockwise direction. So if it is a clockwise direction, we will use the term L. If there is an anti-clockwise direction, it can be D. So due to different rotations of plane perpendicularly, due to different rotations in the plane, right? This is your plane, right? So there will be different rotations in the plane. This is a 3D structure. Different rotations in the plane can be observed in the optical isomers, right? They have the ability. So obviously, your D statement is also correct. So here, third statement and fourth statement is correct. So the answer must be third answer. Understood? So this is what isomers is that we are dealing with. Right? That we are dealing with. So I finished the model paper MCQ. Right? Right now we have completed the isomer part also. Right? Now we have completed the isomer part also. Now the only thing we have completed is we completed IUPAC nomenclature. Isomers is also completed. Now only thing we did the model paper MCQs, right? We did the term paper MCQs, but now we are remaining with the structure. So in order to do the structure, you need to know the reactions that is taking place in each of the functional group. That is a very important concept. Okay. So I'll give you a summary of the reaction for the preparation also. So now what we can do is, now we will go to the new subheading, right? So before that, I would like to advise you a thing that now go do all the past paper questions that you have in the PSR book regarding the basic concept of the organic chemistry, right? Basic compound of organic chemistry. So that's a basic thing that you have, basic concepts of organic chemistry. So that's a important part. So it is there in the structure essay, and then you have in the MCQs also. So how far they have taken the question by understanding through the model paper itself. So this is from Morato paper. So how deeply they have asked. So you have to be in touch with the resource book also, right? You have to be in touch with the resource book. All right. Now finally, we are going to wind up the subtopic isomers. So finally, we are done with the isomers. So as I planned, we will try to finish this organic chemistry by today, inshallah, as much as possible, right? We'll finish it as much as possible. And now what we have to do is, now we will go with the reaction, right? We will go with the reaction. We will take the reaction mechanism as the last part. Now we have to go with the reactions based on it, right? We go with the reactions based on each of the functional group, right? Right. Now I'll go with the reactions based on the functional groups that we have, right? So I'm going to categorize the reactions, right? The organic reactions into two types, right? Note this down on your special points. So one, I'm going to split them as aliphatic reactions, organic reactions, and aromatic organic reactions. So you have aliphatic and aromatic organic reactions basically. So before going to aromatic, let me finish this aliphatic part. Okay. In aliphatic part, my dear students, see here, you are going to have the reactions of alkane, then you have alkene, then you have alkyne. So each of these reactions are completely from the concepts of hydrocarbons, right? Hydrocarbons. The hydrocarbons over here, right? Over here. Then you will have the reactions based on alkyl halides. Alkyl halides. Then you have alcohols, right? Then you have alcohols. Then you have aldehyde, ketones, right? You have aldehyde ketones. Then you have carboxylic acid, ester, right? Ester, I did it separately, right? Halide. Then you have amides, then you have amines, right? So until here you have all these set of reactions. So in this reaction type, I already said you that we are going to split them into aliphatic and aromatic, right? Easy to summarize, right? Right. Now we have all these stuffs here. So we have alkanes, alkynes. So these are the hydrocarbons. Alkyl halides, alcohols, aldehyde, ketones, carboxylic acid, ester, acid halide, amides, and amines respectively. So we have a huge area under this portion. In the aromatic part, my dear students, see here, we will be first talking about the benzene. Okay. Then we will be talking about the toluene, right? We will be talking about toluene. Then we have phenol. We have aniline. Then you have benzene diazonium salt. We have all these people in common: benzene, toluene, phenol, aniline, benzene diazonium salt. So what I'm going to do is, after completing each of these areas, the reactions based on each of the people, this might take around 2 or 3 hours, the reactions, right? So we have that much of reactions, but I'll give an easy method. How I kept it in mind. Right? It's really easy. Now see, we have all these people. We have benzene, toluene, phenol, aniline, benzene diazonium salt. Right. Now, first and foremost, we'll face aliphatic organic reactions now, and then what we will do after the break, after the prayer breaks, we will try to finish up the after lunch break and all. We'll try to finish up the aromatic part. So this is the reactions, organic chemistry's major part, right? This is the organic chemistry's major part. Isomer is a part. So if you know this whole thing, you can score nearly above 70% of the organic marks. Above 70%. I am saying it to you clearly, right? Short, you can get it in one shot, right? No fear. If you have memorized all these reactions, if you have the idea of what is the product that is going to be coming if you add the particular reagent. So each of these people have different reagents. Sometimes those reagents can be same for other people also, but the products can be varied. Understood? So all these reactions are based from your resource book. They have mixed and gave it to you. They have given you both the oxygen base and nitrogen base. So oxygen base means they have put phenol with the alcohols, aldehydes, ketones, carboxylic acid, ester, acetaldehyde, amides. These amides and amines will come under anilene. We are under hydrocarbons. These people will come. Alkanes, alkenes, alkynes, and these people. Alkyl halide also will be there within the hydrocarbons. So it is being mixed up. So to avoid this confusion, I have separated them into different parts. So one is aliphatic, another one is aromatic, right? So now let's go into the alkane based reactions. Okay, now I'll go with the alkane based reactions. So put your new subheading alkanes. Before going into the reactions of alkanes, you know alkane is a hydrocarbon. Obviously, it's a hydrocarbon. Even though if it is a hydrocarbon, under certain molecules, for example, if you take methane, right? Let's say state of matter. In states of matter, we have solid, liquid and gas. We have solid, liquid and gas. There is gas, liquid and solid in the case of alkane. For example, for gas, there is a very famous gas in alkane, methane. That is actually produced by anaerobic bacteria by decomposing them. Right? Decomposing. In decomposing process, ammonia is being, methane is being released. Right? Along with some other gases. Then you have liquid states. Then you have solid. In solid, that is used in daily life. We have naphthalene ball. Kapur bola. Naphthalene balls. So naphthalene balls comes under solid. They sublime. They do sublimation. Like they convert the solid to gas directly. Right? So liquids are also there. You know, octane petrol. Right? Octane 92. You know petrol, right? So we say them as octane 92. So this is also an alkane. This is also an alkane. Okay? This is none other than petrol. Right? So petrol is also liquid. You have gas. In solid, you can keep an example. Naphthalene balls. Naphthalene balls. So you have three states of matter and alkenes. Right? Once you take the secondary interaction of alkanes, right? Secondary interactions of alkanes, you have only LDF. LDF means London dispersion force. So this is the kind of least attractive force that you have, least attractive force, secondary interactive force that you have within the molecules. In most of the molecules you have. Right? So in LDF case, secondary interaction is there. The LDF force is directly proportional to the surface area of the hydrocarbon. The more the bigger the surface area is, right? The more bigger the surface area is, the more the LDF you will have, right? By the major carbon chain. So if this one increases, LDF alkanes also increases. If LDF increases, the boiling point as well as melting point of alkanes are also proportional to LDF. So if this one increases, boiling point and also the melting point will also increase. But you should keep in mind LDF factor is in the most predominant one. Predominant means it is in the most prioritized one. But in the case of boiling point and melting point, you know there's another factor which is called relative molecular mass. So commonly, if the relative molecular mass increases, the boiling point and melting point also increases. Understood? So this is the thing that is okay. So these are the features of alkanes. So in other words, you can say these are saturated hydrocarbons. We call them as saturated hydrocarbons. Now let's go into the reactions. So reactions of alkanes. Now most of the teachers, in a sense, right, they, according to their point of view, they think that giving the preparation method as well as the production method, right, reaction methods of the alkane or any other functional group will help you. But according to me, no. The best method is I will give you all the reactions based on the functional group. Your task it is to find from where you can prepare them. From where you can prepare alkanes by following the next reactions. You can get the link from here. If you do in the method that I say, surely you will understand how to do conversion. It will be very easy if you know where you can produce. Due to my experience, I will say you will get to know that the main junction for all these people to go will be alcohols in the case of aliphatic. In the case of aromatic, you will say diazonium salt will be the main junction based on your paper questions, right? Based on your questions that they have given. Understood? So keep in mind, if you get familiar, you will say alcohols will become the main junction for you. Okay? So I'll just give you the reactions. So the reaction of alkanes are, first one, combustion reaction. There is a common one that you know. So you have, for example, you have methane burning with oxygen to give carbon dioxide gas and with water vapor. So if you balance the equation, you have 2. So here also you have 2, right? So 2 oxygen moles, 2 moles of oxygen is needed for the combustion of methane, right, my dear? Now this is for the combustion of alkanes. Now there is a new reaction that you are going to learn. So that is the second one, halogenation of alkanes, right? Halogenation of alkanes. Halogenation of alkanes. In the case of halogenation, keep in mind, if you take a hydrocarbon, let's say methane, if you take methane and if you put chlorine gas along with H mu, so this is none other than diffused sunlight. You can write in the exam also, diffused sunlight. Diffuse sunlight, right? If you use diffuse sunlight, if you use limited amount of methane over here with chlorine, you will get CH3Cl. But if you put excess, right? Let me write it in the other space. Right? Let me write it in other space. So if we use methane with excess chlorine along with diffuse sunlight, you can get CCl4. Your byproducts after removing with this will be HCl. Here also you will have HCl as your byproduct. Understood? So this much is the reaction of alkanes. This much is the alkanes reaction. That's all. Right? Nothing extra over here. Understood? So our alkanes part is over. The alkanes reaction basis. Oh, only one reaction is there. Here you need to know there is a reaction mechanism. I'll explain it to you at the end of the organic chemistry unit, right? All of the organic chemistry units. So now your alkanes is over. Now we need to go to alkenes. Now we need to go to alkenes. Now we need to go to alkenes. In the alkenes, right? In the alkenes, you have three states of matter. Just like them, you have three states of matter. You have both solid, liquid, and then you have gas. So here you have double bonds. But all features that you have will be applied here. But this is going to be different. Saturated means you need to have only carbon, sigma bonds. So from now on, here you have unsaturated hydrocarbons. Here you have unsaturated hydrocarbons. So this is an important term. You have unsaturated hydrocarbons. Right? Let's go with the reactions of alkenes. Right? Reactions of alkenes. So first things first, usually you know combustion reaction is here. Combustion reaction. So if you have CH2 double bond CH2, right, with oxygen, you will get CO2 and H2O. You have CO2 and H2O. Right? But you can balance the equation later. Now something new is there, right? We will say halogenation. Just like alkanes, you have halogenation. Halogenation. So during halogenation, CH2 double bond CH2, if we use HBr or HCl, right? One of this will get H and one of this will get Br. So you get CH3, CH2, Br or CH3, CH2, Cl. Now the problem arises. Now there is a problem. Once you have three carbons, once you have three carbons. So here you will have a problem. Here two hydrogens were there equally. Here you have 1, here you have 2. But if the case, if you put HBr or HCl, you will have a doubt. One thing is, you will ask, will this one be the answer? Let's say if there's Br only. Or will it be this one? Two answers are possible now. In organic reactions, two chemicals can be possible. Once you do a reaction with the high organic chemistry, there obviously you can have two or more reactions taking place. One will be the major product, another one will be the minor product. So that is the main thing you are going to consider. In exams, they will ask you with the major product. But in 2023, in your chemical calculation, not chemical calculation, in organic chemistry conversions, there you had with a minor product. So it is a must that you need to know about the minor product as well as the major product. Like most of the students got confused after getting the conversion there. Right? So you will ask me, sir, this answer is also possible. Why can't this be? So in order to avoid this problem, a scientist just then came. A scientist came to solve this problem. His name is Markovnikov. Markovnikov. His name is Markovnikov. Right. So his name is Markovnikov. So based on his name, a rule came. Markovnikov rule. What did he say is, the one which has the carbon which has the highest number of hydrogen will get the hydrogen from the other person. What do you mean? Now here you have HBr. In HBr, if you take HBr, let's write the case here, CH11CH2. Now in the case of HBr, you have HNBr, right? According to these two people, bromine is actually highly electronegative. So there's one hydrogen over here, here two hydrogen. So he said this hydrogen must go to this carbon. So inside this there is another concept called stability of carbocation. Stability of carbocation. There is a new term called for you known as stability of carbocation. So this one will come over here. As a result, you will get a carbocation in this case over here. Sometimes this hydrogen can also go and attach over here, right? So this is CH3, CH2, CH2 plus. Now you need to know who is the major product, who is the minor product. Now you have two products over there. Okay, now you need to know the two products that you need to have. In this case, see here, in this center carbon only you have the plus, right? Over here you have this, here you have the plus charge on the terminal carbon. Students, see here, there is a thing called inductive effect. There is a thing called inductive effect. Inductive effect means when there is an alkyl group beside a carbon, there will be a pushing electron cloud. For example, let me deepen this part. Let's continue after the Azan. Right. Assalamu alaikum. Now let's have a prayer break. So let's start the session around 12:45 inshallah. So get ready. Still we have just started the game. So we have to end the game by inshallah around 9 or 10:30 inshallah. We'll try to end the game of the organic chemistry. So until that, stay tuned and we will see you after the break inshallah. Assalamu alaikum.